Hey there, welcome back to Real Analysis. In the previous section 2.8, we were looking at some of the algebraic properties of limits, that is, kind of convenient algebraic tools to manipulate limits to facilitate their computation. Today, we're going to kind of continue along in section 7.8 with similar things, but not looking at equalities between limits, but rather certain inequalities. Or, as the author of our text titles it, we're going to be looking at the order properties of limits. Okay? So let's just dive right in. I've got, I think, three results to cover in this, and we're just going to kind of be doing the epsilon definition of limit in each one of these results. And then after we have them done, they can be put into our toolbox of ways that we can handle limits about inequalities in the future. All right. So let me kind of recenter the screen here, and let's take a look at our first result, the author's theorem 2.18. It says if you take two convergent sequences, we're continuing the same notation from section 2.7. Sn and Tn are their names. They both converge. That is, they both have limits that are real numbers. And then the assumption on these sequences is that for every single n, so term by term, as we say, the sequence Tn dominates the sequence Sn in the sense that its terms are at least as big as Sn. Okay, so we have two convergent sequences, Sn and Tn. Sn's terms are less than or equal to Tn's terms for every single term value, or it's every single term n, pardon me, not term value, but just every single term. And then the statement of the theorem says that, well, the limits of those convergent sequences satisfy the same inequality. Okay, so if term by term, Sn is less than or equal to Tn, well, then the limits will be less than or equal to each other in the same fashion. All right. So how to give the proof? Let's kind of just set up our terminology and quantify all of our variables. So suppose that we've got these two sequences, Sn and Tn. All right, and we're assuming they're convergent. Got to give some notation for their limits. So let's continue the same kind of spirit that we were using in section 2.7 and say that two numbers, S and T, in the real numbers are the limits. Sn converges to the number S, Tn converges to the number T. All right. So that's just kind of establishing the notation, restating the purpose or the goal, rather, the conclusion of the theorem in that notation. I want to show that S is less than or equal to T. Yeah, because we just said, like, well, the limit of Sn we're calling S, the limit of Tn we're calling T. So we want to show that S is less than or equal to T. That's our purpose. So we're going to proceed by a contradictions style argument. How would a contradiction style argument start? Well, you assume the opposite of your conclusion. Let's suppose if S is not less than or equal to T, well, then S is bigger than T. So let's suppose for a contradiction that S is bigger than T, and then let's call their difference in that order, S minus T, which is of course a positive number. Let's call that epsilon. Okay. And now, using the limit definition, Sn is a convergent sequence converging to S. So there must be some index value, I'm going to call it capital N1, so that the difference in the S sequence terms in S would be less than epsilon over 2, provided that the index n exceeds that number n1, right? So that's hopefully becoming kind of a familiar application of this definition of limit. We're using it a lot. So in the same way, because the sequence Tn converges to T, there's some other index value, capital N2, that, oh, pardon me, I kind of have to fix my notes here. Let me kind of make a little bit of room. This difference Tn minus T is also less than epsilon over 2 if n is greater than or equal to n2. So we can have both of those differences small for sufficiently large n. If you want them both to happen at the same time, well, you just take your index capital N to be, or index value capital N to be at least the maximum of those two things. All right. So if you exceed that value of capital N, then we get both of these quantities. Right. So both the quantities Sn minus S is less than epsilon over 2, Tn minus T is less than epsilon over 2. All right. And then I'm just going to manipulate that with absolute value properties. So we have both of these things, right? The difference of Sn minus S is between epsilon over 2 and its opposite. The same for T minus Tn. And if you're carefully following along, and I hope you are, you've noticed that I kind of switched the order of subtraction here, but that's okay, right? Because the absolute value doesn't depend on the order that we subtract. And there's other ways to justify that, but for me, that's the easiest way to think about it. it was kind of a strategic thing because what I'm going to do now is just sort of add those things, or sorry, what am I doing? Yeah, I'm just adding those things together. So I'm taking these two inequalities, or actually there's four inequalities there if I count carefully. It's kind of two compound inequalities, and I'm just summing them. I mean, certainly negative epsilon over 2 over negative epsilon over 2 is epsilon. Same thing over here. And in the middle, I'm not even going to really comment on it. I just did a little bit of algebra. I took this quantity, Sn minus S, I added T minus Tn, and I've just algebraically rearranged it there. So you can stop the video and check my signs, that I should have an Sn with the sign plus and an S with the sign minus, and so on and so on and so on. All right. But now it's time to remember that we wrote above that S minus T, well, that is epsilon. It's the definition of this epsilon in our proof. S minus T was the positive quantity. So I'm just replacing that. And then if I add epsilon to everything, I get these two inequalities. I get that 0 is less than Sn minus Tn, but that's less than 2 epsilon. Okay, so stop the video and check out the algebra. Just kind of following along. It makes it more fun. And now the conclusion is, I'm not going to stop because I want the video to be short. In particular, I'm kind of just focusing my attention on this inequality. If the difference Sn minus Tn is positive, well, that means that Tn is less than Sn. Okay, it's not true for all n, but it is true for n greater than or equal to this capital N. And that's a contradiction. That's a contradiction because we were assuming in our hypothesis of this theorem that Sn was less than or equal to Tn for all n. So that's what I'm contradicting. It cannot be the case that eventually that inequality switches around. So where'd the contradiction come from? It came from the assumption that S was greater than T, so therefore S must be less than or equal to T. Cool. So QED. Here's a little cautionary tale. If you wanted to try to state a similar theorem where you replaced that inequality with a strict inequality, then unfortunately it's false. So it's not true if Sn is strictly less than Tn for all n. That won't force the limits to be strictly less than each other. Right? So the best you'll be able to do over here is say that S would be less than or equal to T. But they could be equal. And I would encourage you to either stop the video right now or at least sometime you can do it. You have some examples that you could put together, put together an example to show this. All right, so my little cautionary symbol over here just means be careful that these order properties with limits as you sort of quote unquote pass to infinity, you often cannot keep these strict inequalities. Okay, you have to kind of pay for them. They might become equal. So I won't say anything else about it right now, but you can try to construct an example. Okay, let's just enjoy a real quick corollary of that fact. It can be handy for us. If you take a convergent sequence, all of whose terms are between two real numbers, alpha and beta. So the author here didn't completely quantify here, but so Sn is a convergent sequence. And if I were writing this, I might say that alpha and beta are two real numbers such that that inequality holds for all n. So the author kind of leaves it to context. It's not a super big sin, but let's just clarify it. Then the statement is saying, well, then the limit would be between alpha and beta. All right, so if all the terms are in the interval alpha to beta, then so's the limit. How do we prove that as a corollary of the above? Well, let's just take two constant sequences. Let's define a sequence A sub n, all of whose terms are alpha. Maybe I'll kind of insert a little detail here. A constant sequence, I'm not going to include the proof here, but you can write it yourself. It's fairly obvious, I think. A constant sequence converges to its constant value. Right, so then I'll just take another Bn, define all of its terms to be beta, then certainly that sequence Bn is convergent and converges to beta. And then you just apply the theorem above a couple of times. Namely, if you kind of transcode this, you have this sequence A sub n, it's less than or equal to Sn. So the theorem above says its limit is less than or equal to the limit of Sn's. Well, that's exactly this inequality. And then if you take the sequence Bn to be the constant sequence beta and apply the theorem above, well, then you get this inequality from the theorem. So you put them both together and you have them both. Nice. So if all of your sequence terms live in an interval between alpha and beta and it's a convergent sequence, the limit lives in that same interval. All right. The final result here of the lecture, I think it's the final result. Every time I say that, I kind of get to the bottom of my notes and forget and realize that I'm wrong. Maybe I should say one of the final results of this lecture is something that you probably recognize from calculus, and that's the squeeze theorem. Certainly, no matter where you took calculus here at HSU, any university in the US, I don't think that there's ever been a first semester calculus course in which somebody doesn't discuss the squeeze theorem, although in a calculus course, it's typically discussed for functions of a continuous variable. So it's a little bit more rich of a context here, but here we're going to state and try to prove the squeeze theorem for sequences. Okay, so why is it called the squeeze theorem? Well, let's oops, talk through it. Sorry about that. My hand touched the wrong button on my iPad. So why is it called the squeeze theorem? What are our hypotheses? We have a couple of sequences, actually three of them. Sn and Tn are assumed to be convergent. Okay, so that's our ingredients. And then not only are they assumed to be convergent, but their limits are assumed to be equal. So I've got two convergent sequences with the same limit. And then I've got a third sequence, okay? I've got a third sequence called xn, and term by term, so for every value of the index n, the terms of the xn sequence are in between the Sn and Tn sequences, like those inequalities there. Okay, so that's the hypothesis. And then what's the conclusion? Well, first of all, the sequence xn also converges. So it's kind of a two-part conclusion. So being trapped between two convergent sequences means that you have, with the same limit, means you're going to converge and you have the same limit as they do. That's the second part of the conclusion. All right. So in other words, if xn is trapped, as I like to say, between two sequences that both have the same limit, well, then it has a limit because it's squeezed between them as n goes to infinity. Okay, maybe you could construct some examples on Desmos if you wanted to kind of draw some plots, and you could watch this squeezing action happen. Maybe we'll do that here in class, but I don't have it ready for this video, and I don't want to do it spontaneously because it'll make the video too long. Okay, so let's check it out. First part of the proof is really just kind of the cast of characters, right? We got to kind of introduce all of our notation, our variables, quantify them, and so on. So let's start getting it. We said we were going to call these sequences Sn and Tn. They converge and they have the same limit. So let's call that limit L. Right, so I'm going to break with the tradition of calling it S and T because S is equal to T, so I'm calling them L. So Sn converges to L, Tn converges to L. And then we take that third sequence, xn, and we make the supposition. Xn's terms are between Sn and Tn for every n. Okay. Now I'll take an arbitrary epsilon. You're expecting that in the proof. I'm trying to prove something about the convergence of a sequence called xn, so I should pick an arbitrarily small number epsilon to use the epsilon definition. But then how am I going to use our hypothesis? Okay, well, since Sn goes to L, I can certainly go out far enough. I'm going to call it the cutoff value capital N1, so that when little n exceeds that, the difference between the S terms in L is less than epsilon. Okay, using the epsilon definition, very used to it now. Similarly, there's some other number, capital N2, some other number that when n exceeds capital N2, the T sequence terms differ from their limit by less than epsilon. Okay, usual device here. I need both of those to be true at the same time. So I take the maximum of those two numbers, N1 and N2. All right, so if, so I'm gonna, that's gonna be the n that I'm gonna condition on. So kind of using the inequalities here, let's notice something. Because xn is between Sn and Tn for every n, not just n's bigger than my capital N, but for every n, by order properties, I can certainly subtract L from all of those things. Okay, so that's just a little bit of algebra preparation. And now let's go out past that maximum. Here, I'm not going to write the absolute values. I'm going to kind of, absolute values come with two inequalities. I'm going to use one of them at a time. So first of all, if n is bigger than or equal to n, then it's bigger than n1. So the difference Sn minus L would be at least as big as minus epsilon. If I kind of zoom out here a little bit, I can kind of point to why that's true. Because Sn minus L in absolute value is less than epsilon. So in particular, its difference is greater than sorry, is less than epsilon. So its difference is greater than negative epsilon. All right. But similarly, Tn minus L is less than epsilon. Why is that true? Well, that's true because n is bigger than n2, and we said the absolute value of Tn minus L is less than epsilon. So in particular, it is 2. Okay, so I have those two things, and I'm just going to throw those two things in together with the inequalities that we already had. All right, so if you kind of want to watch the laser pointer, I'm going to take this Sn minus L, the smallest quantity in this compound inequality. Here it is again. And I'm just going to combine that with the fact that Sn minus L is bigger than negative epsilon. So I'm just kind of trying to underline and color the way I'm thinking about this. Likewise, I'm going to tack that Tn minus L is less than epsilon onto the right-hand side. Xn minus L was between them. Well, that's what the green thing above said. So you can stop the video if you need to and just sort of make sure that you understand how I'm combining all of these inequality statements. And then in the next line, I'm just kind of ignoring the stuff in the middle. I don't really want the information about S's and T's anymore. I'm just trying to focus on the fact that minus epsilon is less than Xn minus L, which is less than epsilon, which of course can be written as an absolute value statement like that. So what have we done at the end of the day? Given an epsilon, we found some capital N that when our index exceeds it, Xn minus L is less than epsilon. Well, that precisely implies that Xn converges to L. So we get both statements at once. Xn's a convergent sequence and it has the same limit that S and T do. Nice. So there's our squeeze theorem. Here's sort of a classic example of this. Maybe this is the one that you could plot on Desmos. Oh, there is another result in this lecture. I'm glad I didn't call the squeeze theorem the last one. Maybe you can stop the video and plot these things on Desmos. This will be kind of cool. I'm somewhat tempted to do it myself, but I'm not going to. I'm going to resist the temptation. So what's the example? Let's take the sequence sine of n over n. Here, sine is the trigonometric function, the y-coordinate of a point on the unit circle with angle n. N's some real number. You can take it sine. Okay, it's not going to be a whole number or anything like that, but still I can do it. I can divide that by n and let n go to infinity, and I want to show that that's equal to 0. And none of the algebraic techniques that we've talked about so far in the course are going to tackle this limit because of the presence of this transcendental trigonometric function sine. So I'm leaning on some stuff that you know from trigonometry, that no matter what n is, the y-coordinate of a point on the unit circle is always at least -1, and it's never more than 1, right? So for every n, the sine function is between there. And so if I divide everything by n, then I get those two inequalities. So if you want to match the notation of the theorem, if I let Sn be -1 over n and Tn be +1 over n, then I've met the hypothesis of the squeeze theorem. Yeah, because this sequence Sn, let me just kind of write it in here in a different color, it converges to 0 as n goes to infinity. It's a constant multiple, -1 of 1 over n, and we've proved 1 over n goes to 0. Tn is 1 over n, it goes to 0. So those two sequences converge and they have the same limit. Okay, so the squeeze theorem says that the thing that's trapped between them also has that limit. Nice. Yeah. Plot it on Desmos. It's a cool plot. Maybe I'll try to talk you into coming to class and say we'll do it then. Okay, maybe this is the last result of this lecture. I don't know. We'll see. Theorem 2.22. I'm not going to give a detailed proof of it, but just rather a sketch. It's going to be kind of handy. It's not really an order statement, but rather exactly what its name says. It's a statement about limits of absolute values. Okay, so it says if you take a convergent sequence with terms called Sn, if you throw absolute values around all those terms, that's a new sequence. You know, if Sn has only positive terms, I guess it's not new, but in general, I mean, putting the absolute value around the terms is gonna change some of the signs of them. So it's a new sequence, which we will just call the absolute value of the sequence Sn. And it also converges, okay? And the statement says that its limit is just the absolute value of whatever Sn's limit was. Or if again you like, or not again, but if you like the kind of poetic, rhythmic statements of theorems like this one says that the limit of the absolute values is the absolute value of the limit. It's a very nice statement, and in fact, it's kind of a special case of something later on in this course when we start talking about functions and continuous functions. The absolute value is an example of a continuous function, and this limit statement is really a special case of a more general statement about limits of continuous functions. Okay, so I'm not going to give the whole proof, just sketching it. So to establish the notation, you got this sequence Sn, and let's say it converges to S. And then it's one of our variants of the triangle inequality. One of those things in like theorem 1.17. I'm not going to write it down because I'm not sure if I'm remembering the number correctly, but it says that if you take the absolute value of a difference of absolute values, it's never any more than the absolute value of the difference. So, or if that didn't make sense, it says that, what I'm writing there. It's a variation of the triangle inequality. Right? But this quantity Sn minus S is less than epsilon for an arbitrary positive epsilon for sufficiently large n because Sn converges to S. Maybe I'll change my comma to a period and write because I'm assuming that. Okay, well, that means that if n is sufficiently large, I can make this quantity less than epsilon. Well, then in particular, I'm making the difference of the absolute value of Sn and S less than epsilon. So you can roll all of that together for a nice proof that the absolute value of Sn is also going to converge to the absolute value of S. Okay, one more. It's just a corollary, and we can kind of enjoy some of your homework. If you take two sequences, Sn and Tn, okay, then we can form new sequences in this kind of cool way too. You make a sequence, maybe if you want, we could give its term some names. Maybe I'll call it Xn. What's the term Xn? Well, it's the maximum of Sn and Tn. So you just term by term, look at the sequences Sn and Tn and pick the bigger one. Or maybe you want to think about this one over here, I'll call it Yn. It's the term by term minimum. Well, then what the theorem statement says is that the limit of Xn, it goes to the maximum of the limits of S and T. And same for minimums. Okay, so it says that if you take the limit of that maximum sequence, you get the maximum of the two limits. If you take the limit of the minimum sequence, you get the minimum of the two limits. We don't have to do this with epsilons and deltas. I mean, not deltas, pardon me. We don't have to do this with epsilons. We have no deltas. Why? Well, because in your homework, right, I remember reading it not long ago from when I'm making this video, that you proved that the maximum of two numbers is given by this kind of algebraic expression. It's the, some of you use this language in your homework, it's the arithmetic mean of the two numbers plus this half of that absolute value, half the distance between them. Likewise, you proved in the same homework problem that, well, and you had to come up with this formula, that the minimum is given by a similar expression, but you subtract. You subtract those things. I'm not going to fix this right now, but I'm kind of doubting myself. Maybe I will try to. I think I might have subtracted in the wrong order. And instead of me trying to think, maybe, can I just check my solutions? You can't see what I'm looking at here. Yeah, no. I doubted myself for no reason. It's correct. Good. I didn't want to have to edit this video. All right. So back to what I'm talking about. How do we prove this? Well, you just combine algebraic and order properties that we just talked about. Okay, because let's just focus on the maximum. The maximum is a sum of, well, constant multiples of absolute values and sums. But we have theorems that say things like, well, the limit of a sum is the sum of the limits. The limit of a constant multiple is the constant multiple of the limits. We just proved, it's why it's coming up right now, the limit of absolute values is the absolute value of the limit. Limit of a difference is the difference of the limits. So you just sort of put together those order properties and algebraic properties, and you have this statement about the maximum. All right. So you prove it by the limit laws and the theorem that we just proved. Minimum is similar. Okay. Thanks for listening. This video got a little long, but I'm going to stop it now.